So a quick look at this from the Pythagorean theorem. We get that that's a 5. And with that, now we're in the position to find the value of all 6 trigonometric functions. Let's start out with the sine of theta. So the sine of theta is going to be the opposite over the hypotenuse, so 3/5. Cosine of theta, 4/5. Tangent of theta is going to be the opposite over the hypotenuse, right? Or it's going to be opposite over the adjacent, so 3/4. You could also do sine divided by cosine. The 5s would cancel, and you'd still end up with 3/4. Let's work with the reciprocal functions now. So the cotangent of theta is going to be 4/3. The secant of theta, 5/4. And the cosecant of theta, 5/3. So just the reciprocals of all those. But now I want to do something a little bit different here. This angle is understood to be a right angle. Now what do we know about the interior angles of a triangle? They always add up to 180. So if this is 90, the remaining 2 angles add up to 90. They're called complementary angles. If 2 angles add up to 90, they're complementary. If they add up to 180, then they're supplementary. I know that this has to be the difference between theta and 90. So I'll call it pi over 2 minus theta. And let's take a look at a few values here. For instance, the cosine of pi over 2 minus theta. Well, the cosine is going to be the adjacent over the hypotenuse, right? Now from this angle, what's the adjacent side? What's its measure going to have? Yeah, the adjacent side has a length of 3. So 3 over the hypotenuse would be 3/5. What else is going to be true? Well, let's take a look at the sine of this angle. So the sine is the opposite over the hypotenuse. From the perspective of this angle, what's the length of the opposite side? 4. So it's going to be 4/5. So it's going to be the sine of pi over 2 minus theta. You see a little bit of a pattern here? Can you make a prediction down here? What am I going to write next? Well, that's kind of what I have here already, is tangent. Cotangent of pi over 2 minus theta. And of course, over here would be the tangent of pi over 2 minus theta. And let's finish this off going all the way down. What do you think is going to be the opposite of this one? What do you think is going to be? It's actually, the fancy term is the cofunction of the secant. Close. Well, it's going to be pi over 2 minus theta cosecant. Good. Cosecant. And likewise, this one's going to be the secant of pi over 2 minus theta. So these are all cofunction identities. And really what it's showing you is the intimate relationship between a lot of these functions. That if you were to take a look at, for instance, the tangent of 12 degrees would be the same thing as the cotangent of 78 degrees. So trying to see if there's a nice summary of those things in the book. No, not seeing it. But here it is. Here's all your identities, your cofunction identities. You don't have to necessarily pay attention to this part right here. Sine is a cofunction with the cosine. Cosine likewise with the sine, tangent and cotangent, secant and cosecant. All these are cofunctions of each other. I just used our triangle here to help prove some of that stuff. Where can you use that? Where can you apply it? Let's take a look at problem number 20. Tangent of 12 degrees minus a cotangent of 78 degrees. Now, after you do a couple problems like this, what's going to catch your eye is this. 12 and 78 add up to 90, right? So you start looking at that going, oh, well, these are cofunctions of each other. So I can rewrite this. I can write that as the tangent of 12 degrees minus, well, what's the cofunction for the cotangent? Tangent. So if I start out with the cotangent of something, it's going to be 90 minus theta, or the tangent of 90 minus 78, tangent of 12 minus a tangent of 12. Hold on while I pull out my graphing calculator for that one. Or I'm kidding. Tangent of 12 minus tangent of 12 is 0. Okay. Let's take a look at problem number 24. Are we okay with this one? Problem 20? All right, so let me come up here and try problem number 24. One plus the tangent squared of 5 degrees minus cosecant squared of 85 degrees. Well, this one's looking tempting / interesting. Let's remind ourselves a little bit about the Pythagorean theorem as it relates to tangent, squared, etc. We'll start with the regular Pythagorean theorem. Sine squared of theta plus cosine squared of theta equals 1. Now, because of this problem where I've got a tangent squared is sine squared over cosine squared, let me divide this through by cosine squared of theta. And that gives me tangent squared of theta plus 1 equals secant squared of theta. Okay, that looks handy to have around. Now, when I start looking at this to try and play with it, I realize I've got a 1 plus tangent squared, but instead of a secant squared, I got a cosecant squared. But the cosecant is 85 degrees. What can I replace that with? Yeah, 90 minus 85, right? It's going to be the secant squared. And you know what? You don't have to write this step, 90 minus 5. If you want to just cut right here to the chase, secant squared of, let's see, that should be 85. Sorry, 90 minus 85 would be 5. If you want to cut from here to here, that's fine. I don't really want to see that step. Now we're almost there. Let's think. If we look at what we have here and what we have here, let's mix things up a little bit. I'd like an expression for tangent squared minus secant squared. So let's see if we can't rearrange this. If I move the secant squared to the other side, I get tangent squared of theta minus secant squared of theta equals, move this to the other side equals -1. What's that telling me about this whole expression then? Yeah, equals -1. So the whole thing turns into a 0. Yay. All right, so that's a little bit of a diversion in terms of the big work in our section here. Vivek?
Can we write 1 plus 10 squared by 2, 6 squared by?
You could have converted this to say the, let's see, it'd be the cotangent of 85. Sure. Oh, okay. You could have, yeah, you can converted this to secant squared of 5. Yeah, that would have been fine. So if this is secant squared of 5, so it's a different way to do it, but it works just as well, maybe even a little bit easier to say, gee, this right here is secant squared of 5. So if you do it that way, then you end up with secant squared of 5 minus secant squared of 5. I'll wait while you get out your calculator. All right, so there you go. Still get 0. So yes, the answer is 0. You certainly could do it that way. Now our goal in this section is to mostly to work with problems that ask you to solve the triangle. And let me start by explaining a little bit more about what that means and our notation for this section and beyond. So let me just draw a nice right triangle. Not trying to draw it in any special way. Now the book might use lowercase letters and uppercase letters. For myself, I'm going to use Greek letters and regular alphabet characters. Yeah, English. You know what? And I think I regret drawing a right triangle because it doesn't necessarily have to be a right triangle in sections 4.2 and beyond. In this section, it does have to be a right triangle. But let me give you the lineup that we're going to use first. But what we're going to do in this section applies only to right triangles, so-called right triangle trigonometry. All right, so I've done my best not to make this look like any special triangle. It's not an equilateral, it's not an isosceles. Our angles would be alpha, beta, and gamma. The Greek ABC. Now, across from each of these angles, you're going to have corresponding regular letters. So across from alpha, you're going to have side A. And across from beta, you're going to have side B. Across from gamma, you're going to have side C. So always these angles and opposite side pairs are going to go together. Our goal in working with these problems is to find all the angles and all the sides so that we know all the information about the triangle. And the cool thing is that you only need to know 3 pieces of information to solve for the other 3 pieces of information. It's going to take us a little while to get there. A lot of work in chapter 4, but we will get there. All right, so let's see an example of that. We'll start with problem number 30. Now, in this section, in section 4.1, C, or actually I should say gamma, is understood to be a 90-degree angle. So, in section 4.1, gamma equals 90 degrees. It's just kind of a given. We're working with right triangles here. So in problem number 30, they tell us B equals 4 and beta equals 10 degrees. Let's write down what we know and what we don't know. So I'm going to use lowercase here, A, B, and C. These are our sides. B was 4. Gamma is understood to be 90. Beta was 10. Now that actually tells us one of our unknowns here, right? If beta is 10, what does alpha have to be? 80, right? So that the whole thing totals up to 180. Let's draw it. Let's draw ourselves this triangle. It doesn't have to really be to scale. In fact, it can be really crappily drawn to scale. It won't matter, just as long as the sides and relevant angles are labeled correctly. So Here's C. That's your 90-degree angle. Then I better make this beta, which is a 10-degree angle. And this would be alpha, which is a 90-degree angle. And I need to label one of these sides 4. 80, thank you. I need to make one of these sides 4. Well, that side that's 4 better be opposite this angle. So that's a 4. And I need to figure out C and A. Well, the interior angles have to add to 180, but the sides don't have to add to anything. There is one thing that's true about the sides. Any two of the sides have to add up to more than the third side. You're not going to be able to solve, you're not going to be able to make a triangle unless, say, these two sides are longer than this one. If that's not the case, then you can't form a triangle. Let's try and see that a little bit. Let's take a look at an extreme. Suppose I have sides A and B of this length and this length. If I put them together, if I had a third side of length C that was equal to these in length, if it equaled these, is there any way that I could form a triangle if this is just long enough to match C? No. These two have to be longer than this one. Always. If that's not the case, then you're not going to be able to form a triangle. How are we going to solve for, say, A here? Well, good question. There's quite a lot of ways you could do this. Let's pick something. Let's pick something that involves a known angle, a known side, and an unknown side. So one of our trigonometric functions. We can do tangent, or we could solve for C if we use the sine. Well, let's go with your first one. Let's take the tangent. Tangent of 10 degrees. So going back to something we've dealt with quite a lot. SOHCAHTOA. All right, I expect that the people will be writing that on their test somewhat frequently from here on out. What do you know about the tangent? Tangent is opposite over adjacent. So in this case, that's 4 over A. That allows us to solve for A. So if I multiply both sides by A, I get A tangent 10 equals 4. Or 4 divided by the tangent of 10 is A. There's one thing you got to be careful of when you calculate this. What is it? Yeah, degrees and radians. Up till now, we've had our calculator pretty much in radians. For convenience, we're going to work in degrees for a lot of the stuff. Practically speaking, it's easier to think in degrees. It's going to be a little bit more friendly. So 4 divided by tangent of 10. Tangent of 10. Let's round our answer to 2 decimal places, 68.5. Now, if you need to work with this number further, to say, all right, well, I got the one side, now I need the other side, then store it. Don't use the rounded version of it. You can hit the store key. Now, when that comes to that point, I'll do that. But for now, 22.69, we'll call it. So 22.69. So whatever side C is, it should be less than, say, 26.69. It has to be less than the sum of those two. Does that make sense? Yeah, that looks reasonable. There's 2 ways that you could figure out side C. What are they? Pythagorean theorem. Nothing wrong with that. That's a nice, friendly way. But in this case, just for the practice, since we already know this one, 22.69, let's see if there's another way that we could solve for, say, side C. let's use the sine. So the sine of 10 degrees is going to be the opposite over the hypotenuse, 4 over c. So that means c times the sine of 10 degrees equals 4. And just to be clear here, I don't want to lose anyone. What did I do to get that? I multiplied both sides by c. On the right-hand side, I got some cancellation, and then I got c times sine of 10 on the left-hand side. Anna, what do I have to do to finish solving for c here? Good. Yeah, divide by sine of 10. So c is 4 divided by the sine of 10. All right, let's see what that is. C, 4 divided by sine of 10. 23 point something, 035. 23.04, we'll call it. Now that makes sense. The hypotenuse has to be the longest side here, and it is by a little bit, not by a lot, but hey, it doesn't have to be the biggest by a lot. It just has to be the biggest, the longest. Okay. How are we looking with that first one, number 30? This is what we're going to do with all of our problems, is try and solve these sides. Solve for the sides and, solve for the angles. What's nice here is that you know that one of the angles is 90 degrees. We'll change that up soon enough. This is 90. That's 80. Oh, it should be alpha. Thank you. Okay. Let's move on to problem number 38. So let's see what's given in 38. We've got C is 10, and then A is 40. This is understood to be 90, and that's it. So we're going to find this, this, and this. Well, beta should be a no-brainer. What's beta? Yeah, it's 50. Remember, this has to add up to 180 degrees, so that's 50. B and C, don't know those. So let's just draw ourselves a little triangle. And the triangle is just for something to look at. It's not necessarily supposed to be drawn to scale. What has to be right is opposite sides and angles have to go together. So opposite this, I have to have the 10. 10 is your hypotenuse. Side A and side B, don't know those. But if I draw this as side B, then this is my 50-degree angle. And if I'm drawing this as side A, then this is alpha equals my 40-degree angle. And now I'm all set. There's a huge variety of ways you can solve here. What you need to do is pick a trigonometric function that involves a known angle, an unknown side, and a known side. And there's just literally dozens of opportunities here. So what do you see? All right, sine of which angle? All right, thanks, Vivek. Sine of 40 degrees. 3. What would the sine of 40 degrees equals? Yeah, so opposite over hypotenuse, so A over 10. And then this is nice. Just multiply both sides by 10, right? Sine of 40 times 10 is A. I also need to figure out what b is. So before I take out my calculator, let's get an expression for b. Dan, can you help me out? What would be an expression that allows me to calculate b? Start by picking an angle. 40 or 50? 50. Okay, so we're going to choose 50. Now, if I want to pick a known side and an unknown side, from the point of view of 50, what are these sides called? That would be the opposite side and then the hypotenuse. So what trigonometric function is that? Opposite over, there you go, sine. Opposite over hypotenuse. So it's the sine of 50 degrees. So again, you're trying to figure out something that involves your known and your unknown. We get 10 times the sine of 50 equals b. And then it's just a matter of taking out your calculator and calculating both of those. I'm going to round my answers to the nearest hundredth. On an exam, I'll tell you where I want it rounded. 10 sine of 40 and 10 sine of 50. Those round to about 6.43 and 7.66. Let's try another one before we do some applications. And it is actually kind of an application. It dovetails nicely with the math and the movie stuff that we were looking at just a minute ago. There's a term that you hear quite often in astronomy, because in astronomy, distances get so far away. I mean, you know, some of the stars that we see in our night sky are just unimaginably far. And one of the things that they talk about is what's called a parsec. And it's a contraction of a couple words, parallax and seconds. It's a parallax second of arc. So I think I've got a nice little picture here pulled up on the web.
That's how fast the Millennium Falcon flies, right?
Yeah. You know what's funny? That's a good blooper, because he did the Kessel run in 12 parsecs. Well, the parsec is a distance. It's like I did the run from Royal Oak to Orchard Ridge campus in 12 miles. Well, no, you do it in maybe 12 minutes or something like that. It's a time that you're looking for. So here we go. Parsec. What its definition is if you were to form a right angle between the Earth and the Sun, and a little tangent out here, looking at a star, if this angle right here is 1 second of arc. You remember 1 second? How was 1 second defined? 1 second was, well, let's see, a degree had how many minutes? 60 minutes. And each minute had 60 seconds. So this is 1/3600th of a degree. It's a ridiculously slim angle. But if you view a star at that angle, then that's 1 parsec. Now, the astronomical unit, that's a distance that we know pretty well. That's 93 million miles. So let's draw ourselves a little triangle and figure out how far away something is if it's 1 arc second away. So let's switch over here. There. So this is way exaggerated, of course. I wonder how far you'd have to go before you get to the width of a human hair. Probably quite a few hundred miles before you get to the width of a human hair. So this distance, this side over here, is 93 million miles. this angle is 1/3600th of a degree. So, let's see, that'd be the sun and Earth. Let's look at it from the point of view of a star. Let's figure out the distance this way. That's 1 parsec. So call that side A. So what do I have to do to involve this known angle, this side, and this side? Tangent, right? If you're taking a look at it from the perspective of the star, this is 1/3600th of a degree. Opposite of that is the 93 million miles. This would be the adjacent side. Opposite over adjacent is the tangent. So I'm going to use a tangent here. Jamel, can you help me set up this? If I set it up with a tangent, what would it look like? All right, 1/3600 of a degree equals Bianca, some help? Good. Opposite over adjacent. So that'd be your opposite side, that'd be your adjacent side. So 93 million over A. If you multiply both sides by A, we'll get A tangent 1/3600th of a degree equals 93 million. And we divide that by tangent, we get 93 million divided by the tangent of 1/3600th of a degree. Calculate that on your calculator. You should get a pretty big number in scientific notation. That number will be 1 parsec. Now I'm getting this off of my calculator, 1.918 E13. Let's just make sure I got enough zeros. Yes, 6 zeros. Are you guys getting that? Do you know what this means, though? It means a lot, right? All right, that's a good way to look at it. What does it actually mean? Good, 1.918. You better not put a negative there. On 10 to the 13th miles. That's a long, long, long ways. Yeah, I think it's a little over 3 light years. Not sure, but it's a long ways. Okay, are we starting to get the feel for what we're doing with these right triangle problems? Because we're going to start moving into a couple application problems. Yes, sir. 1 second or 1. Oh, well, it was a definition. They said, okay, let's just take the slimmest angle that we have a convenient unit for, which is 1 second. So that has a nice definition. And then they said, all right, well, we know this distance, and they just defined it that way. So
how long a light year is?
A light year, well, the speed of light travels at 186,000 miles per second. So times 365.25 days per year times 24 hours in a day times 3,600 seconds, you're going to get a little less than 6 trillion miles in 1 light year. So our nearest star is over 4 light years away. So if you could travel this fast, it would take you 4 years to get to the nearest star. So
The
it's,
star still lit up.
well, the interesting thing is that because it takes light so long to travel these vast distances, you know, even the sun, at a mere 93 million miles, the sunlight that we see is 8 minutes old. So if the sun exploded now, I'd still have time to finish my lecture, which is comforting. It wasn't a promise. All right. A little bit of terminology here as we move into some of the applied problems. So you're going to run into a couple of these. Now the horizontal line that I'm drawing is the horizon. And then sometimes you have sight lines that are above or below the horizon. If your sight line is above the horizon, then this gap here, this angle, is the angle of elevation. And maybe we'll call this one, well, no, I'll just be polite. This one here is the angle of depression. Okay. Let's start with problem number 52. So the person in a small boat offshore from a vertical cliff known to be 100 feet high takes a sighting from the top of the cliff. If the angle of elevation is found to be 25 degrees, how far offshore is the boat? All right, we're going to ignore that the boat is actually floating above the water, or that the line of sight would probably be a few feet above the water. We're going to assume that he jumped in and took his sighting from lake level. Let's draw ourselves a picture. Number 52. So over here we have a cliff. We're going to assume that cliff is nice and vertical. And I know the height of that cliff. The height is 100 feet. Giving ourselves a nice right angle here. What else can I label in terms of my triangle? Yeah, this one right here. That's 25 degrees. Call that A, call that C. What side am I looking for? Am I looking for A or am I looking for C? I'd say A. You're looking how far it is to the shore, not how far you'd have to climb on a rope up to the top. All right, so if we're trying to solve for A, figure out a trigonometric function that involves your known angle, your known side, and your unknown side. And there's probably a couple ways you could work that, especially if you said, oh, okay, well, I know this one, that's going to be, what, 65 degrees, right? So if you count that, boy, then your options really open up. But let's just work with the 25. Yeah, I've got to vote for tangent. Tangent of 25. Tangent of 25, Vivek, what would that be? 100 over A. If you multiply both sides by A and then divide by tangent of 25, you'll get A is 100 over tangent of 25. And then just calculate it to whatever accuracy you need. So 214.45 degrees. Or not degrees. Units would be feet. Okay. So not so bad. If I wanted that, I'd give you like the conversions and stuff like that. If I gave you a problem in meters and I wanted it in feet, I'd give you the conversions. Probably not though. I'll probably stick with whatever units there. But by the way, I think the U.S. and one other country in the world uses feet. Liberia. Liberia. Yeah. Does anyone know where Liberia is? All right. Yeah. All right. Let's try a couple more here. No, it's not. I don't think it is. Yeah, it's in Africa. A lot of I think a lot of cruise ships have Liberian flags. Could be. East British. This is a walking fountain of knowledge. All right. Okay, all right. We'll get a history credit after we're done with this too. History and geography. Why is this? All right, we have to make this the last problem because I don't know what's going wrong with this here. But here's our problem. 58. Security camera in a neighborhood bank is mounted 9 feet on a wall above the floor. What angle of depression should be used if the camera is to be directed at a spot 6 feet above the floor and 12 feet from the wall? All right, I know there's a lot of stuff going on here. Let's see if we can't figure out what it all means. Maybe we'll just finish this up by actually solving the triangle. So let me draw what's going on here. Oops, other way. Problem 58. So the camera is 12 feet up on a wall. So it's right here. Is it near 12 feet? Or is it, no, it's aimed 9 feet above the floor. All right, thank you. So it's 9 feet above the floor. And we're aiming at a point 12 feet away. So I get the wrong side as 12. 9 feet here. 12 feet is this distance. And then 6 feet up. So distance of 6 feet here. So there's 9. This is 12. Well, the triangle that we're going to form is up here at the top. That's also 12. And this distance, we don't need to know, although maybe we will calculate it. What we want to figure out is the angle of depression. This angle here. So if this is 6, this distance here, what's this distance here? 3. Good. Just the difference between 9 and 6. You could, if you wanted to, figure out by the Pythagorean theorem. This would be the square root of 153, but we don't need that. We should be able to do it with the numbers that we have here. So how can we figure out theta? All right, this is a 90-degree angle. Good. So if it wasn't a 90-degree angle, then we couldn't set up something using opposite over hypotenuse or opposite over adjacent, etc. That only works if you have a right triangle. I can't emphasize that enough. It's going to be your downfall in the next 3 sections when we start leaving, or when we leave the comfort and security of a right triangle. Opposite over hypotenuse only works when you're dealing with a right triangle. But that's what we've got right now. So let's continue. What's going to involve this side, and this angle? Tangent. Try and write down what the tangent of theta is going to equal. Derek, do you agree? What's the tangent of theta going to equal?
It's going to be 3 over 12.
So let's go back here. SOHCAHTOA. Tangent is opposite over adjacent. So from the point of view of theta, that's the opposite side, that's the adjacent side. 3 over 12. Tangent of theta is 1/4. But I don't want to know the tangent of theta. I want to know what theta is. How do I solve for theta? Charbel? What's that? Beautiful. If you take the inverse tangent of 1/4, you're going to get theta. And it should be around 14 something. 14. 14.04. Thank you. 14.04 degrees. Okay. How are we looking on that one? Okay. This is a good one to end on because it gave you an example of where we solved for theta as opposed to solving for a side for a change. So for homework, try 19 through 45, 49 through 55, and 61.